Buenas tardes! Our subject today is Introduction to Covariant and Contravariant Tensors. Let M be a differentiable manifold of dimension n. Let U be neighborhood of P in M and a parametrization phi from U subset of Rn to M. Phi at x0 is equal to P. The neighborhood contains an open set, but topology does not matter. What is a tangent vector? It's a function from C inf t from M to R. F is a function from M to R, which is in C inf t. Let TPM equals to the space of points Vp, the tangent space to M at P. Let the bases of TPM be D1, D2, Dn. C dots. D1 is equal to D dx1, C dots Dn is equal to D dxn. Vp is equal to the sum of coordinates Vi at bases di, sum of Vi di. When we apply at f, we calculate Vpf is equals to the sum of Vi partial differential of f composed with phi dxi at x0. Let the differentiable variety manifold Tm be Pt, where P belongs to M and T is in TPM. Tm is the tangent bundle of M. It's also the tensorial fiber 0 covariant and 1 contravariant of M. Let X, a function from M to Tm, a differentiable vectorial field. Xp is in TPM at point P. Xp is a function from C inf t from M to R. X applied to F is a function which belongs to C inf t of M. See the diagram. X from C inf t of M to C inf t of M. It maps F from M to R to XF from M to R. XF maps P to XPF in R, P in M. X also is a function from M to TPM, which maps P in M to XP from C inf Tm to R. XP maps F from M to R to XPF in R. What's Tm? It's the set of applications M to Tm. The vectorial space of differentiable tensorial fields 0, 1. Now, connections from Tm to times Tm to Tm, an interval, a geodesics gamma, and V, a vectorial field, differentiable vectorial field induced by a vector field X in Tm. V is equal X composed with the derivative of gamma in time. Here is the schema. Several atlas in Rn by phi to M. M by X to Tm. An interval V to Tm. An interval I d gamma dt to M. And the diagram commutes. It's not the objective here. The subject now is hyperboloid of two leaves. It's H2 xc sigma tau in R3, tau greater than 0, T2 minus xc2 minus sigma 2 equals to 1. It has Minkowski metric dx1 plus dx2 minus dx3 tensorial symmetric product. Poincaré disk model. B2 is UV in R2. UV plus U2 plus V2 less than 1. And the matrix is the identity multiplied 4 over the square of 1 minus U2 minus V2. Poincaré's half-plane model is H2 double struck, where a hyperboloid is math-cal H2, and math BB H2 is xy in R2 y greater than 0 with matrix identity times 1 over y2. These three models are isometric, but it's not our subject here. Our subject is pull back and push forward. Push! Let f be a differentiable application between differentiable manifolds f from M to N. Tm in Tk the M from M and Tn in Tk from N. You know what it is? It's a generalization of our Tm. P is in M. Fp is Q in N. Wi is equal to dFpVi. Therefore, pullback of F in Tn is equal to Tm if Tpm applied to k vectors v1 c dots vk is equal to the tensor Tn at point key applied to vectors w1 c dots wk. P inverted is equal to f from mg2 to ng1 as one isometry of the disco to hyperboloid. P1. So let's turn back. P is from hyperboloid to the ball. P inverted is from the ball to hyperboloid. Let G be F inverted. Therefore, P is G from ng1 to mg2. F pullback applied to g1 is equal to g2 implies pullback g1 VV is equal to g1 push forward of F applied at V. Another time, push forward of F applied to V is equal to G1 applied to WW is equal to the inner product WWW at point F of P is equal to VV at P is equal to G2VV. The tangent vectors V in Tm, W in Tn, P in M, Q in F of P are in N. Definition: W is equal to push forward of V if WQ is equal to dFpVp is equal to dFgq VGQ. Therefore, U is G push forward from W if UP is equal to DGQ WQ equal to DGFP GFP. Another definition: pullback of F onto W is equal V if VP is equal to DGQ WQ equals to push forward of GW at point Q is equal to UQ, where we like when DGQ is equal to DFP inverted. This is an analysis theorem consequence of the chain rule. The derivative of F bold G is the derivative of the identity, which is the identity. Well, we saw that Tm is equal to G2VV equals to VVP equals to DFPV at point Q equals to push forward of F G1VV equals to pull back of F Tn, because TPMVV is equal to TKNWW. Conclusion: pull back the Tn VV is equal to pull Tn applied to push forward of F at V, push forward of F at V. Now we're gonna prove that if W is equal push forward of V, then for all function F, V applied at F circ F is equal to WF circ big F. Don't worry! What's VP applied at G? It's V1 GU at UV plus V2 GV UV, where G is F circ big F. Do you understand that? Let's turn back to the model. Here's UV, U2 plus V2 less than 1. At point P, we have V1 and V2, and we have GU, GV. Who is G? G is 4 over 1 minus U2 minus V2 squared. It has a derivative related to U and the derivative related to V. So we're writing at VP at G is V1 F CU plus V1 F sigma U plus V1 F tau U plus V2 F CV plus V2 F sigma V plus V2 F tau V. We are transforming UV to Xi sigma tau by the function P. Where is P? P inverted of UV is equal to Xi sigma tau equals to 2 over 1 minus U2 minus V2 times U. First coordinate. Second coordinate, 2V over 1 minus U2 minus V2. Third coordinate, 1 plus U2 plus V2 over 1 minus U2 minus V2. So we have WQ equals to DFPVP. It's two matrices as seen here. V1 XU, V2 XV, V1 sigma U plus V2 XV, V1 tau U plus V2 tau V. What's done here? The differential of F at a point V applied to a vector Vp is the Jacobian applied to V1, V2. Double QF is equal to rewriting who is V1 XU FC V1 FC XU plus V1 F sigma U. We only rearranged the terms V1 V2 V1 V2 V1 V2 1 1 1 2 2 2. Therefore, VP of F circ big F is equal to double Q of F. So you see, this VP is equal to this VP, and this calculation above is equal to this calculation in the middle. V1 V2 V1 V2 V1 V2 is equal to V1 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 V2 V2 V2. Generally, let dim M plus codimension of M equals to delta M. Dimension of N plus codimension of N equals to delta N. First line, you express VPG at the basis of tau M, and you find delta M per segments. Here we found 6 segments, 3 plus 3. Line 2, chain rule. Chain rule, delta M plus delta N per segments. 1, 2, 3, 1, 2, 3, 4, 5, 6. So here 2 segments and here 6 segments. Line 3, express WQ as a product of Jacobian times column vector V. Here is expressed. Line 4, you apply WQ to F and conclude. A robot learns that in Delphi, indeed. And black square. Now let's prove definition. Let F from N to N, a differentiable application between differentiable varieties, manifolds, Tm in Tk of M, Tn in Tk of N. P in M, F of P equals to Q in N, Wi equals to dfp Vi. Therefore, pullback of F at Tn equals to Tm if Tpm applied to V1 C dots Vk is equal to Tkn applied to W1 C dots Wk. Theorem: pullback of F multiplied by Tn is equal to F circ big F pullback of F applied to Tn. Now we're going to use the diagrams. Let Un equals to Ftn. So here's Un, here's F, here's Tn. Define Tm as by F pullback at Tn is equal to Tm if and only if Tpm V1 Vk is equal to Tkn W1 Wk with Wi equals to dfp Vi. Analogously, define Um by pullback of F of Un is equal to if and only if Upm V1 C dots Vk equals to Ukn W1 Wk equals to Ftkn W1 Wk with Wi equals to dfp Vi. The diagrams commute. What's push forward of Tm? It's Tn. F multiplied F push forward of Ftm is equal to Un. G multiplied by Tm is equal to Um. Therefore, push forward of F to GTm is equal to Un. We want to show that begin with Tm, apply push forward, multiply by F. It's the same that multiply by F equals to F circ big F and apply push forward. Initially, let the isometry of the model of the disk to the model of hyperboloid. P inverted UV is equal to Xi sigma tau. Vamos ver, let's see. V, não, VXi is equal to V1 XU plus V2 XV. We express the tangent vector V at Xi. Also, V at sigma and also V at tau, V1 tau U plus V2 tau V. V is in TP-B2. We apply push forward of P inverted and get W, big W, Vc, V sigma, V tau in the tangent space of the hyperboloid at Q. We apply F and we have the great Y, F V Xi, F V sigma, F V tau. And we pull back by P inverted X. X equals to GV. G multiplied by V is also at the tangent bundle TP B2. The tangent space. The tangent. Yes. Tangent plane to B2 at point P. The frame. Third diagram. P inverted is from the ball to the hyperboloid. F is from the hyperboloid to R. G is from the ball to R. F circ P inverted is equal to G. Fourth diagram. Big F is from M to N. F is from N to R. G is from M to R, where M is equal to B2 and N is equal to H2, the hyperboloid. To calculate the pullback of big Y equals to F V Xi, F V sigma, F V tau equals to F to the sum, F to the sum, F to V1 T tau U plus V2 tau V. What is big Y at point Q? It's F at point Xi sigma tau multiplied by V1 Xu plus V2 Xv. And we do it 3 times for 3 coordinates. Xu sigma U tau U Xv sigma V tau V. When we calculate the pullback, we're going to find the X. Big X is equal to F circ P inverted at V1 and F circ P inverted at V2, 2 coordinates, is a tangent field which in point P is xp equal to F at Xi sigma tau applied to V1, F Xi sigma tau multiplied by V2. YQ is the differential of P inverted at point P applied to XP. That's not obvious. So this is not this. Jacobian above and below. Jacobian here and Jacobian. Jacobian when doing the pullback, the push forward above, and the Jacobian from X to Y. V and W and X and big Y. Now let's go up to Vm in T0 to M. What's Vm? It's a function from M to T0 to M. It's a generalization of our tangent bundle Tm. Vm maps each point P to P T line. P is the same P and T line is a function in T02 of TPM. This means that T line is maps TPM times TPM to R. And we denote T0 to TPM. T line maps V1, V2, TPM, TPM to VPM, V1, V2, which is a real number. Remembering that the tangent vectors satisfy VP from C infinity of M to R and maps VPF, VP maps F to VPF. In T01M, T line V1 is written alpha du plus beta dv at V1. So this is the most simple case, 0, 1. Here I should simplify. V1 equals to V2 equals to V, W1 equals to W2 equals to W. VPM at V1, V2 equals to alpha m du, all times du at V1, V2 plus b beta m du, all times dv, V1, V2 plus gamma m dv, all times du, V1, V2 plus delta m dv, all times dv at V1, V2. The second most simple case, the basis of T01M is du dv. The basis of T02 of M is du du, du dv, dv du, dv dv. We're gonna need the dimension of the spaces where M is immersed. Delta M, dimension of M plus codimension of M. Delta n is the dimension of n plus the codimension of n. Generally, we express TPM at the basis d1 O times c dots O times d uk with all indexes varying from 1 to delta m. We call the coordinates alpha im with I varying from 1 to delta m elevated to power to q, k. VPM at point v1 at two vectors v1, v2 is alpha m v11, v21 plus beta m v11, v22 plus gamma m v12, v21 plus delta m v12, v22. Double key qn at vectors w1, w2 is equal to VPM v1, v2. with wi equals to Jacobian of p inverted at point P times vi. wi1 equals to xu vi1 plus xv vi2. What is wi2? Sigma u sigma v. What is wi3? Tau u tau v. Generally, t key m is at vectors w1 c dots wk is equal to tpm at vectors v1 c dots vk. It's the Jacobian of big F. WQN at W1 W2 equals to A1 dxc dxc plus B1 dxc d sigma. And here goes on. C1, A2, B2, C2, A3, B3, C3. And the basis is xi, xi sigma, xi tau, sigma xi, sigma sigma, sigma tau, tau xi, tau sigma, and tau tau. Generally, we express t qn at the basis. dx1 all times c dots dxk with all indexes varying from 1 to delta n. We call the coordinates of big A I with I varying from 1 to delta n power to k. Here's power, here not. Double key n applied to w1 w2 equals to a1 a2 a1 b1 c1 a2 b2 c2 a3 b3 c3 at w11 w21 1122 1123 1221 1222 1223 1321 1322 1323. Double Q n at points w1 w2, rearranging, substituting that line, the Jacobian above, gives that confusion. The long line not confused. A1 xu xv xu xv b1 xu xv sigma u sigma v c1 xu xv tau u tau v plus c3 tau u v11 tau v v12 tau u v21 tau v v22. Generally, it's possible also to exchange every way I by the Jacobians of f big F times vi. What comes next? Who is v11? du. Who is v21? du. I will not speak that, just contemplate that. WQN at way 1, W1, W2 equals to A1 CU 2 power to 2 plus B1 CU sigma U plus C1 sigma U ta U. We are grouped all du. We are grouped all du dv. We are grouped all dv du. And we are grouped all dv dv. And the main system is alpha m equals to this coefficient, beta m equals to second coefficient, gamma m equals to third coefficient, and delta n equals to the fourth coefficient, which are alpha n of ABC, beta n of ABC, gamma n of ABC, and delta n of ABC. Generally, we have alpha I, m equals to alpha n of A1, big A1, C dots, big A, J, with J equals to delta n powered to k, and with I varying from 1 to delta m powered to k. Who is alpha? That old coordinate from VPM. VPM equals to double QN. Alpha equals to alpha. And now let's multiply by F. Big Y QN W1 W2 equals to F big W QN W1 W2. Generally, UQN is equal to F TQN at the same WI. Now we have to calculate the push forward of XPM, and we will find big YQN. Contemplate it. By one side we have F, alpha M, F, beta M, F, gamma M, F, delta M, and at the other side we have F, A1, A2, A3, F, B1, B2, B3, F, C1, C2, C3. Generally, we might calculate the push forward of TPM equals to a column F from x1, x delta n alpha IM with I varying from n to delta m power to k, and find UKN equals to F x1 xj big A powered to index big K with j equals to delta n powered to k, and with big K varying from 1 to delta n powered to k. What's XPM V1 V2? Y QN W1 W2, and generally UPM is equal to UKN at respective vectors. Just imagine, who is the big YQN? Analogously, it is QRS. Here is ABC. Here is QRS. And I do the accounts, the calculus, and the system is just like here. There, F A alpha M equals to alpha n, F beta M equals to beta n, F gamma M equals to gamma n, F gamma n, delta M equals to delta n. Generally, F from x1 x delta n alpha IM equals to alpha IN B1 B big K with big K equals to delta n powered to K, and with I varying from 1 to delta m powered to K. But I know who is alpha M. Alpha M is, by that equation, the main system. Alpha N ABC. F alpha N ABC, alpha N QRS. F beta N, beta N. F gamma N, gamma N. F delta N, delta N. Generally, F from x1, x delta N alpha IN A1 A big K equals to da-da-da. And what we have here? A polynomial is identically null if and only if every coefficient are null. Just take a look at the main system. It's almost a polynomial in Q equals to C sigma tau both sides. Using that strategy above, This implies that FA equals 2Q, FB equals 2R, and FC equals 2S. Generally, main system is exactly a polynomial each side by the entrances of Jacobian. So this is the Jacobian, Xu sigma u, Xu tau u. Second degree. Using the polynomial strategy, this implies FA big A equals to big B, quod erat demonstrandum. What we should demonstrate? We begin at Tm. We applied push forward and multiply by F. It's the same that multiply by G and apply push forward. What happens if L greater than 0? Out of intimal reform, there is no salvation at all. This is an exercise. L greater than 0. Now let's show that the pullback of F circ G is equal to pullback of F circ pullback of F. Let G be a function of L from L to M, P line in L, G of P line equals to P in M. Let H equals to F circ G. Pullback of F at Tn equals to Tm, if and only if Tpm equals to Tkn, with Wi equals to dFpVi. G pullback at Tm equals to Tbk, if and only if Tp line k equals to Tpm, with Vi equals to dGp line Uy. H pullback of Tn equals to Tbq if and only if Tp line q equals to Tq1 Tkn, with Wi equals to dHp line Ui. We want to show that Wi is the same, dFp. Vi is the same, dHp line Ui. But by the definition of Vi and big H, dFp at dJp line at Ui is equal to the differential of F circ G at P line applied to Ui. Just take a look. It follows immediately from the chain rule. For exercise, consider L greater than 0. Pullback of identity is equal to identity. Demonstração! Identity pullback of Tn equals to Tm if and only if applied to the same vectors v1, vk. So we must abstract the vectors. Tpm equals to Tpn. So we can and might abstract the p. At every p, at every v1, at every vk, Tm equals to Tn. At every p, at every v, pullback of identity at Tn equals to Tn. At every t, pullback of identity is equal to identity. Now we're going to show that the pullback of all times the tensorial product of Tn with Un is the tensorial product of the pullback of Tn times the pullback of Un. Let F from m to n differentiable application between differentiable manifolds Tm in Tkm, Tn in Tkn, P in M, f of P equals to Q in N, Wi equals to dfp Vi. Therefore, f pullback Tn equals to Tm if Tpm equals to Tkn. We express Tpm at the basis du1, duk, and we call the coordinates of alpha im. We express upm at the basis du1, duk, and we call the coordinates beta im. Therefore, vpm equals to tpm all times upm equals to the sum alpha im beta jm du1 duk all times du1 duk in t2k of m. No entry. We express tkn at the basis dx1 dxk with all the indexes from 1 to delta n. We call the coordinates ai, and we express ukn at the same basis, and we call the coordinates big A, big B, I. Therefore, VQN equals to TQN all times UQN equals to the sum of AI BJs at in T2K of N. We want to show that the push forward of F in VPM is equal to VQN. By definition, VPM at V1 V2K equals to VQN W1 W2K. We exchange WI by DFP VI, and alpha IM is a transformation I1 from A1 to AJ. Also, beta AM is the same transformation at B1 BJ, and also gamma KM is the transformation another transformation K2 from C1 to CL with L equals to 2 delta n power to 2k. We know that gamma km equals to alpha im beta jm. CL is big AI big BJ. Alpha im beta jm is a transformation of A's times a transformation of B's. It's another transformation too of AB's, A1B1, ALBL, from 1 to delta n powered 2k. So you see an example of low level. Now our last case of hyperboloid. What is a transformation of A1, A2, A3, and what is a transformation of B1, B2, B3? Multiply both. You'll get the polynomial of degree always 4 equals to 2k, 3 power to 2k monomials. There is an only linear form of combining monomials of degree k and generating monomials of degree 2k, multiplying the coefficients. The theorem holds by linearity and by the fact that all monomials of main system, they are the same degree k. black square. What about L greater than 0? Let's go up to Vm in T2 0m. Vm is application from M to T2 0m. It maps a point P to the same P and T line. T line is in T20 TPM. T line is in the dual. The dual TPM times the dual from TPM to R. Omega 1, omega 2 are mapped to VPM omega 1, omega 2. Remembering that the covectors, the tangent covectors satisfy omega P are functions from C infinity of M to R. They map F to omega P of F. In T10M, T line W1 equals to alpha du plus beta dv at omega 1. So we are repeating, right? The basis, most simply speaking, is du dt, du dv. And here I should have been simplified. The omega 1 equals omega 2 equals to omega, eta 1 equals to eta 2 equals to eta. VPM, omega 1, omega 2 are expressed as alpha m, beta m, gamma m, delta m at the basis du du, du dv, dv du, dv dv. Codimension, generally we express TPM at the basis du1, duk, and we call the coordinates alpha im with I varying from m to delta m power 2k. VPM omega 1 omega 2 equals to alpha m, beta m, gamma m, delta m. WKN eta 1, eta 2, VPM with pullback of F eta I equals to omega I equals to the transpose matrix of the Jacobian of P inverted at point P multiplied by eta I. So you see, omega I1 is equal to Cu eta u tau u, and omega I2 are Cv sigma v tau v. Generally, first line is Tn at etas equals to Tpm at omegas, and appears the transpose of the Jacobian matrix of big F. WQN at etas is equal to A1, A2, A3, A4, A5, A6, A7, A8, A9 at the basis dx1, dxk, and we call the coordinates AI. Now VPM at omegas is alpha m multiplied by Cu sigma u tau u, Cu sigma u tau u, C dots, eta 21, eta 22, eta 23. Generally, it's also possible to exchange all omega i's by the transposes of the Jacobian matrices of F times eta I. VPM at omegas are alphas, betas, gammas, and deltas. VPM is B1, B2, B3, B4, B5, B6, B7, B8, B9, written on that basis. And main system is A1 equals AI equals to BI at alpha m, beta m, gamma m, delta m from 1 to 9. Generally, Line 2. Multiply by g. xpm at omegas is equal to gvpm at omegas. Generally, upm at omegas is equal to gtpm at omegas. And we now have to calculate the push forward of xpm and find yqn. Line 3. Generally, we might calculate the push forward of tpm f alpha and find uqn fa with j equals to delta n power 2k and bk varying from 1 to delta n power 2k. xpm equals to yqn. Generally, upm equals to uqn. Just imagine I define xpm analogously by C1, C9. I do the calculus and the system is fai equals to ci. Generally, fai equals to ci. I know who is alpha I. fbi equals to ci. Generally, fbi equals to ci. And the polynomial is identically null if and only if all its coefficients are null. We take a look at main system. It's almost a polynomial in Q equals to xi sigma tau each side. And using polynomial strategy, fb equals to c. Generally, fb equals to c. Line 4, we conclude that un equals to ftn quod erat demonstrandum. Your exercise now is consider k and l greater than 1. What I should have done is fix k and l 0, 1, 0, 0, 1, 1 and show by mathematical induction that kl leads to kl plus 1 and kl leads to k plus 1 l. Out of charity, there is no salvation at all.